Hello, and welcome to Week 8 of the Genomics in the Cloud Book Club. I'm your host, KT Picard. In today's meeting, we continue building on best practices, this time talking about somatic variant discovery. Last week, we covered germline variant discovery, and this week extends those principles. We'll go through the examples in the book, and we'll have the resources at the end, and if there's time, time for open discussion and questions. So Chapter 7, Best Practices for Somatic Variant Discovery. So as Geraldine, one of the authors, has pointed out, there probably is nothing more universal than cancer. All of us are in 10 different time zones, and it cuts across. Cancer is one of those things that does cut across time zones. We're going to start with talking about tumor progression and how we get here, because somatic variation is really the thing we talk about most cancer is the thing we talk about most when we talk about somatic variation. And just as a reminder from last week, somatic versus germline, again, somatic being acquired, and germline are those mutations that were inherited. So again, mostly talking about cancer. Of those mutations, though, only about 5 to 10% of those mutations in cancer are generally thought to be inherited from a parent. Most of the other 90% or so happens over a person's lifetime, either through environment or something else that triggers cancer. What you're looking at here is a picture of the progression of cancer. On the left, along the bottom would be time, and a normal is the gray line. And what you're seeing is as things progress, we have mutations that we call driver mutations. And those mutations then change the nature of cell division. Normally within the cell, there's other proteins that keep those driver mutations in check, cancer inhibitors so that they don't get out of hand. Other mutations, passenger mutations, are along for the ride that may or may not have deleterious effects. But generally what's going on here is that as the cancer then moves into this pre-malignant or dysplastic phase in orange, and then as it moves on, it becomes malignant, or in the worst case, metastatic, where it moves throughout the body. What we find in cancer is that many of these cancers are very heterogeneous, meaning that there's a large variation in the genetic makeup of the tumor or lesion. And you'll see that's reflected there on the picture on the right. And this is an example of cells that look like little corn cob kernels, but they actually represent different kinds of cells, from the healthy ones that are kind of light tan, and then all the way to the blue ones that are metastatic. When we work with tumors, we're trying to capture both samples of the tumor that are potentially cancerous, and also what we'd like to have is a normal sample, and you'll see that circled there with around blood, where you could capture a normal sample. And this helps us to filter out the signal from the noise, as it were. When we do these samples, though, they are terribly vulnerable to contamination and error. In breast cancer, for example, you may sample the tumor 3 to 6 times, depending on what you're using, like a core needle biopsy, or if you're using vacuum assisted, you may sample 8 to 10 times. Nevertheless, you're trying to make sure that you're sampling in the area of the tumor and not bringing in healthy tissue at the same time, because that tends to confound the results. So a lot of what we're going to talk about today is separating signal from noise and building up a healthy, if you will, interpretation of somatic variation. Sometimes it's not possible, as we said, to do this tumor-normal or TN analysis. And usually it's because we don't have the matched normal that you see on the bottom of the picture. In some cases, it's biologically impossible to get a normal. For example, in some blood-borne cancers, those mutations typically reach all the tissues in the body, and so it's not possible to do a tumor and normal. You can do workflow on the tumor sample without a paired normal. The results will be noisier because you have to rely on a different germline population so that you can use that as a resource to exclude the person's own germline genome. And that's the first part of what we'll talk about, is the steps that we use to do that. So that leads us to best practices for somatic short variant discovery. You'll see the diagram here. It's a bit of an eye chart test, but I'll walk you through the first parts of it. At the top, we have the BAM files for both the tumor and the normal. We have a couple of other inputs, the Mutect2 panel of normals. Mutect is the mutation caller that's similar to the call variants that we looked at in the last chapter. This one's specific to mutations that are used in somatic calling. The other M2 is sometimes it's referred to. Other input is the genotype, the population frequency that we use to call against, and we'll get into those details in a minute. Once we get into the calling, then those variants go through a number of filtering steps. We'll walk through those as well. And the last part of this is we talk about functionally annotating this, and this is the first part where we talk about, structural variation or SNVs and, we talk about single nucleotide variations and indels. The second part of this talk is where we'll actually get into somatic copy number alterations or CNAs, and we'll talk about those two different workflows. Let's see, so the first part is around this panel of normals. I will skip through this part. It's made for you. It shows you the steps in the book on how you create a panel of normals. Usually it's created from at least 40 people who are unrelated to the person who has the tumor. The Broad uses a panel of normals that are comprised of several hundred samples. So in the first step, we run Mutect2 in tumor-only mode on the normal that we selected to be in our panel of normals. The output, as you can see here, is a BCF file of calls that are either most likely artifacts or germline variants. In the next step, we consolidate those per normal BCFs using Genomics DB as we did in the last chapter. And finally, we extract the calls that are relevant to the goals of the panel of normals. In this case, we're using the Nomad database, as you can see here, which has variant calls for more than 100,000 people. This database provides allele frequencies for each variant call that we use to gauge the likelihood that a variant call might be a germline variant rather than a recurring artifact. In our example PON, the file contains a subset from a few chromosomes, chromosome 6, chromosome 11, and chromosome 17. And here you'll see an output from the panel of normals. And here we're just focusing on the first entries in chromosome 6. And you can see the reference and the alternate for that has a high enough allele frequency that it shows up in the panel of normals. Step 2 is running Mutect2 on the tumor-normal pair. And you can see the commands in there. In this case, we're going to be using 40 publicly available normal samples from the 1000 Genomes project. And we're going to be doing this in the Somatic directory if you're using Google Cloud. I'll fire this up in just a minute because it takes about 5 minutes to run. Mutect2 produces a BCF file containing those possible variant calls as well as a bamout file. As we talked about in the last session, the bamout can be used for visualizing intermediate results. Mutect2 also aligns reads. So if you want to read data, that's why we use the bamout. So I'm going to pause right here and fire this off so that we can come back to it in a moment. If you haven't done this already, if you go back a few weeks, you can get into your own Google Cloud account. Right now, I've fired up my Google Cloud instance, and I'm running GAT in a Docker. And I'm going to grab the first command here for running Mutect2, and you can see it here. So I'll fire that off and then walk through the rest of the workflow, and we'll come back to this slide, and we'll come back to the virtual machine in a minute. Okay, so after we get our output of the somatic calls, the next step is to estimate cross-sample contamination. And this is done by getting Pileup summaries, not only from the normal, as you see on the top, but also from the tumor on the bottom. Even small amounts of contamination between samples confuse the caller, which will lead to false positives. And we estimate the amount of contamination in every sample. We flag the mutation calls as an allelic fraction equal to or smaller than the contamination rate. So basically, we're using it as a floor to identify things that might be suspicious. So the way that we do this is we identify homozygous variant sites in the normal, and that chooses which sites to look at in the tumor. Then we evaluate how much contamination we might have in the tumor based on the fraction of reads that support the reference allele at those sites. Since they should be homozygous, any reference reads that are present must have come from something, and that must be the contamination there. So we look at biallelic sites that are found within this common variation database. In this case, we're using the GATK exome database. And for every site in that subset, we look at pileups and identify those sites that are homozygous in both the tumor and matched normal. So I've run that, and I'll show you the output in a little bit, but in real time. But this is what it looks like, the pileups. And this is the head of the file. As I mentioned, it starts with chromosome 6, and it gives you some things like the counts and the allele frequencies, which are here on the right. We'll use this in the next step to calculate the contamination estimate. And the you can see the command there. So we provide both of those summary tables to the calculator tool. And viewing the output then shows that the level of contamination is estimated to be, as you can see here, 1.15%, and it has an error of 0.19%. And this percentage here, 1.15%, will be the floor for detecting low frequency somatic events. So our next step is to filter the Mutect calls. And in this step, we'll filter based on the probability that a variant is a somatic mutation. It takes into account the germline population frequencies that we looked at, the contamination estimate that we just calculated, and the read orientation statistics that we computed earlier. So you can see these the stats, the table, and the reference, and the mutation calls, and the output again is this filtered list of somatic calls. We'll come back and we'll look at visualization of what came out of this. This is a visualization of TP53, a gene that provides instructions for making a protein called tumor protein P53 or P53 to, it's a tumor suppressor. And what we're looking at here is a place in chromosome 17 where there's a C to T variant, and it's showing up in the tumor, but not the normal. Generally speaking, when TP53 is not working as expected, the protein is not made, and that can be a problem for the proliferation of cells because there's no way to catch that. So the last bit is annotating those. You can get, so we kind of got a picture of what it might look like by visualizing it inside of IGB. The next step is to use functional annotation to get more information about what might be going on. And GAT has a cute name called Funcotator for the functional annotator, and it will show predicted functional effects and their significance. So in this case, we use transcripts. Those annotation resources come from sources like GenCode. It captures information in a standardized format called the gene transfer format, or GTF. It also contains a list of the compiled annotation resources that can be used with Funcotator. You can also use your own custom resources if you want. It outputs a VCF file by default. You can also make the output a mutation annotation format, or MAF file. These files are used extensively by the cancer genomics community. Today we'll be using the VCF file. So once you run that, you get the output, and you can take a look at it. This is what it looks like. And we're actually looking now for a particular spot on chromosome 17 that's specific to TP53. And the single nucleotide variation is indeed a C to T substitution that creates a missense mutation. In this particular part of the file, there are 124 mutation records. 21 of them were noted as being missense, and 10 of those were passing all filters. So it looks very, very likely now that we can call a mutation in this particular location for TP53 having a missense mutation, explaining why there's a lack of P53 tumor suppressor protein. So let's walk back to our machine, and it is finished. I'll go back now to some of the other commands. We can walk through them. So again, our first was running Mutect2 on the tumor-normal pair. It came out with this list of somatic calls. We now need to estimate the cross-sample contamination. So we'll do that. And we do that both for the tumor and normal. This is good. Geraldine makes a point of this in the book. You can see it says it's a beta tool and not ready for use in production. She points out that a lot of the tools have moved from beta into production and have not had those messages removed, and to not let that worry you too much. But it always is good to check the documentation to get the current status of any particular tool. In this case, we've run both of them, and then as you can see here, we can run these to get the output that has the allele frequencies, both for the tumor and, for the normal and also for the tumor. So moving on, our next step was to calculate the contamination estimate. So we'll run that command. And that gives us a table then. We'll show it quickly. And you can see here again the contamination as 1.15% contamination and an error of 0.19%. The next step is we need to filter those calls using some various inputs that we talked about. So I'll run that. And then finally, we'll annotate them with Funcotator. And this adds information like it might be a missense or what have you. So it's actually now showing and calling out on those variations. And we can take a look then at those at the output, and you can see the word missense showing up multiple times as we talked about. If you took this apart, you'd find that 10 of them passed the QC controls. And the other thing that you can see a lot of in here is TP53, and that's again referring to the gene that is in question. So that takes us through the first part of the chapter, which is around calling somatic variations. The next part of the chapter goes into somatic copy number alterations. Let me blow this back up. And so we actually have a different approach for this part of the chapter. And the main reason that it's different is that we have to look at the relative amounts of sequence in the sample of interest, and it has to be measured relative to itself. What we're measuring is the copy ratio rather than the actual sequence data, and we use that as a proxy for the consequence of copy number alterations, or CNAs. So what you're looking at in this slide is the difference between copy number and copy ratio. There's the normal diploid form like we are in humans, and the chromatids there, you have, again, this is inside potentially a tumor cell. So the trisomy is really reflective of a cancer cell with multiple copies of itself. Indeed, though, it's the same idea. We often think of Down syndrome with trisomy in chromosome 21, I think it is. It's the same idea, but in this case, we're looking at copy number and copy ratio. So in a normal case, the copy number is 2 because there are 2 chromatids, and the copy ratio is 1. But anytime it's elevated above 1, then we start to get concerned that there's a kind of copy number alteration that we need to worry about. Graphically illustrated here in this karyotyping, still widely used here in the U.S. When in the absence of sequencing. This is the visual representation of the genome. And optically, we can see here on the left a normal cell line with chromosomes. Here's a cancer cell line for a breast cancer tumor HCC 1954, which we use in the examples. And you can see multiple copies of different chromosomes, where there should normally be 2. There may be 6 or more in some cases. So obviously something is not right, and that gives you the difference between cancer and normal cells. For copy numbers, it's even more important now as we're starting to filter these things out. It's important to have a panel of normals that's composed of normals that are closely matching the technical profile. It's important to note that the copy number panel of normals is a completely different a completely different panel of normals than the one that we used in short variant analysis. So as we go through this, we'll be making a panel of normals, but it's very different than the one that we used in the first part of the talk. That leads us to best practices workflow for copy number discovery. And I can walk through it a little bit here. So again, we have the tumor-normal. We're collecting coverages or read counts. We'll be denoising that afterwards. There's that panel of normals we talked about. From the denoised coverage, we'll segment them and we'll make some plots. And from that segmented coverage, we'll make calls and we'll make some plots from there. And those segments we can output in a tab delimited file or tab separated file to look at the end. So the first step of this, as I mentioned, is we'll create a preprocessed list of intervals. This is used, the preprocessing intervals uses a merging rule that controls whether or not GATK merges adjacent intervals for processing. That's the overlapping only. Bin length we set to 0 because we're using exome data. It would be larger if you're using whole genome. And the padding gives you some buffer between reads. So it's our first step is calculating coverage counts. The second step is calculating, collecting those reads then. We count how many reads start within each interval. Normally this tool writes data in something called the HDF5 format, but we'll use tab separated values or TSV because it's easier to read, and that's the TSV5 here. Again, the IMR is the same as the interval merging rule. And again, we're using the overlapping only rule. And then when you output this, the first column is the chromosome. The second and third are the start and stop of the target region. And the fourth column is the count of reads that are overlapping at that target. So that gives you kind of a blurry picture that we need to refine. What you're looking at on the bottom is a layout of chromosomes. The gray is a demarcator of first chromosome. The white would be second chromosome. The gray again, third chromosome. The centromeres are designated with this dotted line. And you can see all the way through, there's just a lot of noise here. And so really the next step we need to do is to look at this target and filter it and try to make sense of it. Because as you can see, there's lots of targets and a whole genome, lots of bins. So that's the next part of this journey is applying denoising. Before we apply the denoising, there's this whole creation, as I mentioned, of this CNA panel of normals. It's covered in the book, and it's not something we'll show online because it takes a long time. But it is important to note that the best practices recommendation is to use 40 more normal samples if you can. Here we're denoising the sample case read counts by first standardizing the read counts by the median number of counts and then in the panel of normals, and that produces the copy ratios. And next, we're applying the denoising algorithm to these standardized ratios using a principal component analysis of the PoN. So it's a two-step process, and these are the CNA plots after those two steps. You can see that the range of values in the second image is tighter than the first, and it's certainly a lot clearer than the slide we saw a few slides ago, the image we saw a few slides ago, which was terribly blurry. So now this starts to get at, you can see standardized copy ratio on the vertical axis, and the denoised copy ratio here, it's running from 0 to 12, and now we see some things that are above 2, which is of interest. Next, we're performing segmentation and calling the CNAs. It's the last step in the process. We create these segments using the Gaussian kernel. The Gaussian kernel binary segments this thing, and then we can plot this to model segments using the second command. And this is the output. There's a lot going on here. In this case, we see actually 235 predicted segments. And the authors point out that this is an extreme situation. Again, this is this tumor HCC 1143. In many cases, it's not quite as complicated, but it gives you a picture of, of what it can be, where things are copy ratio 1, but then there's areas that are much higher than that. And it gives us pointers to where the issues might be happening. Finally, then we make those calls and we use finding those segments, the ratio segments, and this tool adds a column to this file, and the column then, the segment file, it marks amplifications with the plus sign, it marks deletions with the minus sign, and neutral segments with a 0, as you can see down here at the bottom. And I'm guessing that we're in a woman's chromosome because the last thing here at the tail of the file is chromosome X, which is consistent. So for the full progression then, we've now taken those kind of Manhattan plots, sometimes they're called, and we've turned them, because they look like the skyline of Manhattan, up and down. We turn that on its side, 90 degrees on the right. On the left panel, you can see the raw copy counts per target or bin, and we're moving along as we go through the pipeline. The next and the second and third panels are showing standard and the denoised counts. So again, becoming clearer and sharper. The fourth panel shows the segmentation and the calling result, including, and as you can see, one whole chromosome amplification and one whole chromosome deletion. On the rightmost panel, you'll see a minor allele fraction. It's calculated using some additional procedures that are outlined in the book. Indeed, there are additional steps that you have to run to label which chromosomes are the additions and deletions that again, we don't have time to do. But anyway, this is really the final result of this copy number. So we got a few minutes here. We'll run that. So our first step is calculating the coverage counts. Great. Our next step is collecting read counts. And again, we're capturing only those that are overlapping. And when that's finished, we'll take a look at the last part of that file. I should say, if you haven't, take a look a few chapters back, again, as I mentioned, to get access to Google Cloud to free credits and a free trial of the cloud. So we're typing this out, and now we get a list of the chromosomes, the start and stop, and the number of counts. With that, then we can denoise those counts. And that again was a two-step process. And we'll then plot those. And that creates the plot that we saw that had, you know, kind of the blue and green where things were getting a little clearer. And the final part is actually creating the segments then that's going to be used to make the final calls. And then with those segments, we'll get the copy ratios. Here's the second part of the sampling. It does a really nice job of letting you know where you are. Right now, if you can read it, it says 75 of 100 samples generated. And so it's finishing up then. Always nice to have a cup of tea or coffee to when you're doing bioinformatics. Okay, terrific. And getting down to the end here, we're calling those segments. And then as you see, we'll type that out. And then this is the tail end of it, where we're showing, again, the amplification, the deletion, and a neutral segment there. That actually is the walkthrough of the chapter. It's rather intense, and so there's some additional resources to help you through this, including the basic documentation on germline somatic variant discovery. Again, this is for SNVs and Indels, or SNV should be. A little more about Mutect2, about the Funcotator, and more about functional annotations in general. Finally, everything you wanted to know about the HDF5 file format, and some broader documentation around somatic copy number discovery. And then this video, which I liked, which got into more detail about somatic variant discovery, covers a lot of the same material that we do here, but here we do it in at a great clip. So we'll pause here for a minute. I want to say thanks for following along. Next week, we get into 4 weeks of workflow discussions. Lynn Langet is our guest speaker next week, and she'll be walking us through the workflow little data language, I guess. Yeah. So anyway, please join us for that, and we'll get into some really good discussions we've been having on Slack around this as well. So I'll stop sharing and pause for questions. Looks like we got some things in the chat. Did everyone get a chance to? Oh, and Geraldine, you joined us. Hello and welcome.
Lovely to be here. I caught the tail end of your presentation there. Very nice.
Great, thanks. Actually, we've got some things in the chat, but I think I'm going to preempt it and ask one question if you don't mind. I'm going to share again. There was a color question I had for you, and it's in this last slide here. There we go. No, this one. So this was the progression from raw numbers to final calls. And this last one had I wondered if the colors were significant, if it was a loss of function, or I wasn't sure what the difference between blue and orange was.
Oh, I'm embarrassed if that's not actually specified in the book. The orange and blue in those visuals is not meaningful. It's just beyond the fact, it's just alternating by segments to be able to see more clearly when there's a switch between segments where the ratio is very similar, so that you can still see that they're different segments according to the algorithm. But there's no actual significance to whether any given one is blue or orange.
Okay, great. Well, I appreciate that. Thank you. And it may be, you know, like many things that I've noticed, is that sometimes I miss things in the book, so it may well be there. Let's see. Oh, great. So you answered. Oh, I see. You've already been answering questions. This is great. Okay, so I'm looking at the chat.
I had a related question actually to your question about the plots. In what seems at the end that on all the plots, the centromeres are represented. Is that just an aesthetic choice, or is there a reason for representing them?
Honestly, that's not something that I have questioned in the past. I believe it's just informational, that it's in some cases you can see events near the centromere. Things get a little weird near centromeres in general. And so I think it's helpful to know that this is where the centromere is, and if things get weird around there, it's probably because of that. And it can help the analysts decide whether to dig deeper or not, depending. I think that's the rationale, but can't guarantee.
Okay, thanks.
Thanks for the question, Matthew.
And you can usually see that there's kind of a gap in coverage anyway. The centromere itself is typically not covered. Do we want to discuss briefly the questions that were in the chat, just in case there's some remaining uncertainties? Because this is a question that we get very, very frequently, is like, what do you use to make the panel of normals? And it's a hard one. And it always comes back to what is the PoN for? And it's really for ferreting out these technical issues that are causing bias. In the case of the short variants, you know, SNVs and Indels, it's a matter of what's causing SNVs and Indels during prep stages and those stages. In the case of copy number alterations, it's, you know, what's biasing the amount of coverage that you have for a particular region, because we know that things like the amount of GC base pairs versus AT is going to tend to lead to different amount of coverage and things like that because of biochemical effects. And so, and there are a variety of other kind of sources of artifacts. And so the panel of normals is really intended to ferret those things out and be able to produce some baselines, right? So if you have 100 or so samples with the matched normals, it's okay to take the matched normals to make the panel of normals. If you don't, or if you have much smaller numbers, then you need to find some other samples that are appropriate. At the Broad, in the production pipelines, because we have access to a lot of samples and they're all processed the same way, we can make panels of normals from just private data that we have available. And so if you're part of a sequencing facility, you can make panels of normals from data that you have from research samples like that. In the clinical world, I know things are a little different in terms of what you can use, but that's kind of the basic idea. Otherwise, you can try to find public data, and for example, the example panel of normal that we provide with GATK documentation is based, if I recall correctly, on 1,000 genomes data. But there you get into the problem that if your data was generated differently, then the panel of normals baseline will be to some degree different from the baseline that you should have for your samples. And so the more difference, the more distance, and the less effective the denoising will be. So that's kind of the risk that you're running. In the case of, I'm looking at Ian's latest like follow-up question. I would say, you know, as long as you're within the Illumina environment, one might presume that's the technical similarities are going to be close enough. I can't tell you exactly, and that's the kind of thing where ideally you'd want to do some testing. You might not have the possibility of doing that. I think those are close enough, but there is a risk. If for whatever reason going from the HiSeq 500 to the NovaSeq, there's something that affects coverage bias distribution, you could end up with some funny effects. But it's definitely better than nothing, and it's better than getting something completely external, random. I hope that answers the question.
So let's build on that. So we were talking about this technical profile, and you were talking about you know, different sequencers, different protocols for preparation, and then you know, Ian's question was you know, his samples came from, a couple of them were different sample prep kits and different machines. Are there kind of best practices? You know, is there a line there for a best practice for what's considered, you know, a technical profile that is reasonably the same? So, for example, he mentions, you know, one is from a prep kit from V5 to V6. So this gets very complicated because every sequencer has its own prep kit, and then you're going across sequencers. So it's a, you know, it's a problem in a high dimensional space, right? So how do you, Ian, I just so you know, Ian said he can't talk because his kids are asleep, and I understand. Anyway, maybe you could talk to that a little bit more in terms of giving us a sense of, you know, where you draw the line.
This is the age-old, it depends, or at least I'm not aware that our folks have done any systematic evaluations of version to version to version. We have, for educational purposes, I know there was one tutorial where we looked at a few differences between two different PoNs. But the simple answer is we haven't done a systematic evaluation between like generations of kits and machines and things like that. I think it'd be a really interesting thing for the field if somebody wanted to go ahead and do that. I think it would be a great resource, and it would totally make a very useful paper if somebody wanted to do that. It's in the case of the GATK development team, the constraint there is that there's a lot of work to do. And because we have access to everything we need in-house, it's difficult to justify putting in the effort to do this, even though it would obviously be beneficial to everybody. But we do answer to specific grants and other things that give us money to do work. But I think it would be a wonderful resource if somebody wanted to do a systematic evaluation.
Thank you for that. Other questions or comments from our members? Well, Geraldine, I wanted to say that, you know, I don't know if you caught, as I was running the commands, I ran one set and then talked and ran the other set. Absolutely flawless as usual. No challenges at all in the execution. So thank you again for a really well-written book that works. I can't tell you, my wife's studying some coursework right now, and it's so frustrating because all the links to the data are stale and nothing works, and it's really frustrating. So it's so cool that we can just use a copy of your repo to get this data, and it just really makes for a positive experience. when people watch this, and we get, I don't know if you know, but the numbers of subscribers on YouTube continues to grow by the week. They get to watch this and see that indeed it works as advertised. So, and kudos to you and to Brian.
Thank you for that. That's the thing that we were most paranoid about, was making sure that everything would work out of the box. And things will change over time to the best practices, and we do plan to update the content. And so even if somebody gets an older version of the book, which is what, like nine months old at this point,
Right.
we will have like change log. We have a change log and things like that. So that is the big thing. We want to keep it just working like that for people, because it's essential. So thank you.
Right, and things change so fast in our field. It's amazing, changes to links and documentation even, and you've managed to work that in the book by using shortcuts that you can change as needed as the documentation changes. So again, very clever and very useful. In the documentation, because we're kind of static at a point in time, I include the URLs that are current as of this talk. But as always, those links will change over time. So the good news is the GAT documentation has a nice search function, and there's a lot of documentation when it comes to somatic crawling, as I learned, and I found it easy to find inside of the toolkit. So thank you for that.
I'll add one note, is that I believe it was in November, there was the team did a webinar about some of the latest innovations to the short variants pipeline with Mutect2. I believe there's no differences in the commands and the tools that you run, but there's a few algorithmic improvements, and I believe they discussed that in the webinar from last November.
Very good, thank you. Well, I'll ask the last question then. You talked earlier about the names of commands inside of GATK being very practical. They kind of say what they do, but except Funcotator. And I'm wondering how that came to pass, that there's a fun story behind how the Funcotator got its name.
I don't recall exactly. I think that's the one that they came up with while I was on parental leave. I think so. I mean, I used to work much more directly with GATK. Now I work kind of on other projects. And I stay associated with GATK as much as I can, but not as closely. And so I don't want to make it sound like I take credit for all the naming and so on. Most of the time it's independently of me, but it happens that we got some new folks and they were very enthusiastic. And among other things, they made that tool. And they got a little carried away with wanting to name things. The copy number, the germline copy number variants too, there were some long email threads of people suggesting all kinds of names. But I was around for that one. And I think, again, it wasn't just me, but there were some discussions about what's actually helpful for people versus fun for the developers.
Right.
But Funcotator is still, it's all right, because there's still Oncotator. Oh, and I should say, it's actually part of the history is that it is the successor to a tool that was called Oncotator for oncology annotator. But the task for Funcotator was to expand it to be all functional annotation, not just in the cancer space. But yeah, I would still have preferred something more obviously, obviously named, but it's kind of fun, so they get a pass.
Well, it's got the word fun in it. It's hard to go wrong with that. But this is the take home, folks. Is you leave engineers alone for a little while, you know, you go on parental leave, and this is what happens. So there
Exactly.
you are.
Can't leave them alone for a minute.
No, we're all better off. Right. That's great. Okay. Well, I think we'll call it a day. Unless there's one last question, we have a few more minutes just in case. If you've been waiting, if you've been dying to ask a question about somatic variant calling, this is your shining moment. Anyway, really good discussion in the chat window today. Well, we'll keep it going on Slack. And as we'll move next, now we'll move out of variant calling. Now we'll move into workflow. Most of what we've been doing, all of what we've been doing is on single sample, and the workflows that we'll be getting into next allow us to move into the world of doing this across many, many samples. And now begins a journey of, I think, about a month of working at scale, starting with Whittle and moving all the way through Cromwell and Terra. We have some guest speakers that I'm very excited about, and I'm working on some more. So we'll keep that going. I want to thank everyone for joining us today. Appreciate your time, and we'll see you again next week. Thanks for joining us. Geraldine, thanks for joining us too.
Thank you. Thank you for organizing, as always. Pleasure.